It's a great pleasure to be visiting my alma mater, and a great honor to speak at this very special event, honoring my professor, my PhD advisor from years ago. Thank you, Matt. The title of the talk is Universal Quantifiers, Non-Continuous Operators, and their Fixed Points. So the objective of the talk is to find a fixed point. Plan of the talk, introduction, historical remarks, preliminaries, related concepts, getting to the point, fixing the point, contemplating or admiring the fixed point, finally conclusion, which would be weaker without other fixed points of view. The theorem which is fundamental for this consideration belongs to Knaster and Tarski, and I really envy Knaster, who in almost 100 years ago came up with this profoundly deep result, which is so general that it's bound to find thousands and thousands of applications in the future. In 1955, Tarski generalized the result from the setup of the Boolean algebra of sets to abstract Boolean algebras. So if X is a complete lattice, F an order-preserving function on X, then the set of fixed points of F is a complete lattice. As a corollary, we obtain immediately that there exists the least fixed point and the greatest fixed point. This is because a complete lattice must be non-empty. Important applications exist for this theorem in formal semantics of programming languages. Some related results. We need to define a directed set. Let X be a poset, D, which is a subset, is directed if it is non-empty, and then the finite subset has an upper bound in D. Equivalently, you have to consider two-element subsets. The notation which I'm going to use is the following. The union symbol D will stand for the least upper bound, 0 for the least element of the lattice, LFP will stand for least fixed point, and F upper OK will be the case iteration of F on 0. While iterating, we use the infinite joins on limit originals. An operator F on the complete lattice is called continuous if for every directed subset, if you take the image of the subset and then the big join, then this is the same as taking the join and then applying the operator. Here is a second theorem which we'll be concerned with. If X is a complete lattice and F is a continuous operator, then very easily F is order preserving, but more importantly, the least fixed point of F can be reached in omega iterations from the bottom of the lattice, in Cantabile iterations. But in this talk, actually, I want to consider a situation in which some operators are non-continuous, and this theorem, unfortunately, will not apply. Melvin Fitting wrote extensively on fixed points. There are at least 8 research papers on the subject written by him. The last one, I believe, is a survey, Fixed Point Semantics for Logic Programming, a survey. And that paper discusses the following major areas. Apt van Emden Kowalski semantics for Horn programs, which dates back to 76. Three-valued Kripke-Klini fitting semantics, which was introduced by Fitting in 85. Stable model semantics in two-valid settings of Gelfand-Lifshitz, 88, well-funded semantics from 91, three-value stable semantics of Przymusiński, and semantics using bilattices and down-up for-valued logic formulated by Fitting in 91. All these theories in the survey are related to what I'm going to consider. I will say a little more on Kripke-Klebe fitting semantics later on. The basic theory for all these considerations is still the first on the previous slide, Abt, Von and Kowalski, and the concepts that are the following. We take a language which is an arbitrary countable first-order language without equality, but with at least one individual constant. That's a technical condition, but which I always have been finding very unpleasant and and I always wanted to do something about it. I didn't like this addition of a single constant, which was required for technical reasons. Statements are Horn clauses of the form A provided B1 through N and so on through Bn, where all the A's and B's are atomic formulas. A program P is a finite set of Horn clauses. L-Brand universe, U sub L, is the set of all ground atoms of the language. L-Brand base is the set of all ground atomic formulas of L, and L-Brand interpretations are first-order relational structures determined by subsets of the L-Brand base. So these models, these structures always have a L-Brand universe as the universe. L-Brand model of P is an interpretation that is a model for P, and we define an operator associated with the program P. The operator T sub P is on the lattice of L-Brand interpretations, and given an interpretation I, it looks for Horn clauses A provided B such that B is true in I under some valuation V, and if so, the head of the clause with this valuation becomes a member of the value of the operator. Von and Kowalski proved that for this operator, the least fixed point the minimal L-Brand model of the program P is the same as the least fixed point of P, and because of some of the previous result, it can be reached in omega iterations. To comment on this result, it is important to have this reachability in omega steps, because if you want to compute pieces of the model using, let's say, SLD resolution, then you can iterate on a finite number of times to compute a single piece. So it was crucial for the context in which this result was obtained that we have this reachability in omega steps. In our work, we'll do the following. We'll consider a constructive completion of a program with positive negation. We'll be considering positive programs with equality constraints. So the statements will be of the form A provided B, but B will be allowed to contain universal and existential quantifiers, conjunctions, disjunctions, true, false, but no negation. However, equality will be allowed, and actually equality will be allowed in arbitrarily complex formulas, possibly negated. We'll define a hierarchy of such programs. I will deal with the problem of defining the L-Brand universe where one extra constant has been added for technical reasons, it will be now done differently, and the universe will also have different logical properties. And finally, we'll be using only two valid interpretations, so this is unlike fitting with Kripke-Kleene fitting semantics. There will be least fixed point theorem concerning operators which are non-continuous but still reach the fixed point in omega steps. And finally, to complete the considerations, I will show that no other class of the hierarchy of programs has the same property. Languages in these considerations will be always first-order languages with equality. I will assume finitely, or that they have finitely countable many predicate symbols. There will be only finitely many function symbols, including individual constants. Here's the hierarchy of positive formulas. The symbols are the same which are used in the arithmetical hierarchy of sets, but there is really nothing deep about this arrangement. It's just a way of looking at how many quantifiers are there in the formula and in what order. Plus delta 0, plus sigma 0, plus pi 0 are all the positive formulas without quantifiers. Then, if you want to take the next step, plus delta and plus 1, you take the previous sigma and pi and close under conjunction and disjunction. For the next sigma n plus 1, you take this delta n plus 1 and close under conjunctions, disjunctions, and existential quantifier. Similarly for pi sub n plus 1, and finally delta plus delta omega is the class of all positive formulas. Comment in this hierarchy, negation P is not a positive formula. I mean, obviously it's equivalent to a positive formula, but in general this kind of equivalence is not effective, so the definition doesn't allow it as a positive formula.
The definition of the negation, except the quality of the negation. What is this P here?
No, I'm just pointing, you're completely right.
So that means double negation of equality is not considered a positive.
This is a hierarchy of formulas which involve only positive connectives and quantifiers, no negation. However, I wanted to make a remark just to explain that if somebody would think that negation P could be classified, it isn't.
Are you treating equality and inequality as really independent predicates, which happen to be disjoint? That's all you're saying about it.
I mean, it's...
Let me ask you.
This equality is just a negation of equality with a classical negation. This equality is not a separate predicate. It's just a negation of equality. Then hierarchy of arbitrary formulas. So now formulas which possibly involve negation. This is conceptually similar, but the conditions are more complex because I'm classifying formulas which are not necessarily in the Prenex form. Here are some comments on these hierarchies. The classes of this hierarchy, of the last hierarchy, are not, well, actually either hierarchy, are not closed under equivalence. For instance, this formula, if you look at how the quantifiers are arranged, it is pi 2. And it's definitely not a delta 0 formula because it has quantifiers. This formula is however equivalent to this, and that is equivalent to true, which is delta 0. However, the formula definitely doesn't belong to delta 0, so classes are not closed under equivalence. This is how This is the mental picture I carry of the hierarchy. And some more comments. What is sigma 1? That's the class of all formulas with no negative occurrences of the existential quantifier and no positive occurrences of the universal quantifier. Similarly for pi 1 with the reversing the roles of the quantifiers. Point 2, every sigma sub n formula is effectively equivalent to a Prenex formula sigma n. So n blocks of quantifiers in alternating existential and universal, followed by a formula without quantifiers. Similarly for pi sub n, and you can characterize also delta sub n. Then the classes of positive formulas can be obtained by intersecting the corresponding class of arbitrary formulas with the class of all positive formulas. So these are all expected properties. And now I'll be introducing equality constraints and positive formulas with such constraints. Equality constraint that's an arbitrary formula with no predicate symbols except equality. I want to place equality constraints in a positive formula. So let's consider a positive formula with predicate variables. Second order. Replace these predicate variables by equality constraints. What results will be called a positive formula with equality constraints. So positive formulas with equality constraints may contain negations, the negations which apply to equality. This is an interesting class of formulas because it shares many good features which positive formulas have. But still some negation is allowed. The hierarchy of positive formulas with equality constraints is arranged in the following way. Just giving examples, if you start from formula B of P1 through Pn, so P1 through Pn are predicate variables, and if that's a sigma plus sigma 1 formula, and now if you take equality constraints S1 through Sn, which are delta omega formulas, then the resulting formula after the substitution is called plus sigma 1 formula with delta omega equality constraints. Another important class which we'll be considering is that of plus omega formulas with plus omega equality constraints. So in the second class there are no occurrences of negation at all, but the first class may have some occurrences of negation. The classification of formulas in this hierarchy is not unique. Let's look at this formula. This could be taken as a plus pi 1 formula with delta 0 equality constraints, or alternatively as plus delta 0 formula with pi 1 equality constraints. And now, slight change of the topic, open and closed universes. To explain this, I'm considering a very simple program. P of A provided true, and P of B provided true. Now, one way of assigning declarative meaning to a program is by using Clark's completion. And that's a set of formulas. Actually, I'll define it, I'll mention the definition later, but it's in general, it's a set of formulas obtained from the program. In this particular case, it would amount to turning the implications in the program into equivalences. Now, the completion proves P of A and also proves P of B. However, it doesn't prove for all x, P of x. And this suggests that in the intended domain, we have more elements than just A and B. And otherwise, the universal closure of P would be true. So the domain is open. It contains more elements than just the constants mentioned in the program. Another take on this. Let's consider SLD resolution, which underlies Prolog. For this program, if you ask a query about P of A, Prolog says yes. If you ask about P of B, Prolog says yes. However, if you ask P of X, you do not get the identity substitution, and this means this puts in question whether there are any other elements in consideration beyond A and B. Also, the standard definition of Herbert universe assumes that the universe consists of just ground terms from the language, in this case just A and B, nothing else. The universe is closed here. So there's a discrepancy between how we view the program declaratively or even through the SLD procedure and what the Herbert universe tells us. And to change this, I'm defining an open version of Herbert universe. This will be called an omega Herbert universe. And the symbol will be U super omega. Now, to do that, I'm adding to the language L a countable set of new individual constants. These constants will be called free elements. They will not occur in the program. The formulas which we will consider will not contain them, but they will be available in the universe. With this approach, one can define notions analogous to those of Herbert interpretations and obtain results similar to those of Van Emden and Kowalski and Abt. SLD resolution has a success set which coincides with the interpretation reached in omega steps, which is the same as least fixed point, which is the minimal model for P, and this coincides with ground statements implied by P. Now, coming back to the hierarchies, there will be positive programs with equality constraints. So the statements in these programs will be of the form A provided B, where A is atomic but non-trivial. B will be a positive formula with equality constraints such that variables of B, free variables of B, form a subset of free variables of A. And then positive program with equality constraints is any finite set of such statements. So in these programs, equality constraints incorporate some negative information into otherwise positive bodies of the statements. Also, a comment, the condition of variables implies that P of x provided Q of xy is not a statement in this sense. It becomes a statement if you put the existential quantifier in the body.
Otherwise, y would be interpreted quantified in the present.
And actually, the first formula, if you apply universal quantifier on the outside of the entire implication, that is equivalent to this.
So why is it not a positive statement?
The definition is restricted. The definition insists on the left-hand side having variables which are a subset of the right-hand side. but it's not difficult to achieve this state by this kind of mechanism, always putting the existential quantifier. And some technical concepts that developed first by Clark. I don't think Clark really called anything like that Clark's form, but the concept is his. So Clark's form for a program is a program in which for every predicate there is exactly one statement with that predicate occurring in the head. Not two statements, not zero. Clark's transformation transforms into Clark's form. Basically, if you have many formulas with the same head, form the disjunction of the bodies. And you may need to deal with the terms which occur in the head. So if there was a term t, now it becomes p of x provided there exists y such that x equals t and the body. And then you join all such bodies. Clark also defined completion of a program, which amounts to term multiplications into equivalences. But we'll be using a different approach to completing a program. And let's notice that for any formula, you can apply De Morgan rules and obtain an equivalent formula in which the negations occur only at the atomic level. So the formula obtained from B in this way will be denoted by B super dm. The notion which will be crucial for this consideration is that of constructive negation, found in papers of Chang, Mushinsky, and independently I write the same thing. For a language L, construct a new language which contains additional predicate symbols p dash for every predicate p except equality. So if there are predicates p, q, and r, now we have p, q, and r, but also p dash, q, r, q dash, and should I say bar, p bar, q bar, and r bar. And then form two new sets of formulas, starting from those in Clark's completion. A provided B in the De Morgan form, and also in the second set, negation of A. I'm sorry, there are typos here. Because actually, instead of negation A, I wanted A bar provided negation of B turned into the Morgan form, but after that you still need to replace negated atoms by the predicate symbols with bars. So that's a typo. So here's an example of this. Let's start with this program with three clauses, and now in the class we'll have positive part and negative part, and they are related as shown here. One interesting thing to notice that in this context, you can build arbitrary chains of quantifiers. The formulas which are at the bottom of the screen follow from the completion obtained this way. And now, what I'm going to present has a relation to Kripke-Kleene fitting semantics. Quoting from the survey paper of fitting, for a computability, for a computationally meaningful notion of finite failure, the semantic counterpart of the iterating the operator omega steps from the top of the lattice. I'm not reading this correctly. For a computationally meaningful notion of finite failure, the semantic counterpart is the result of iterating this operator omega steps from the top of the lattice. Unfortunately, doing this gives us something which in general is not a fixed point. Moreover, it can be pi1 complete, which means uncomputable. We choose to work with the largest fixed point. Now, I'm going to use not standard omega, not standard Hilbert universes, but omega Hilbert universes, the open version. And curiously, this eliminates the problem. Greatest fixed point is obtainable for, at least for, let's talk for now about Horn programs. It's obtainable in omega steps. But there are other classes which have this property as well. Then fitting associates with a program P an operator phi sub P, which is analogous to the T operator, but on three-valued interpretations. And these involve valuations of clauses of ground version of P. And three-valued clean strong logic is used with the logical values of true, false, and undefined. On the other hand, I'm going to use constructive negation, as explained before, instead of the three-valued logic. My feeling is that programmers, if this thing ever is going to be used for programming, programmers do not think in three-valued logic. However, it's entirely possible to have a preprocessor which takes a computer program and produces the positive version P+, and then even finds what class of the hierarchy it depends on. And then the programmer can inspect this version of the program and continue the work. And finally, the important thing is that for negated queries, at least if you consider a negative query with a positive, with a Horn program, negation as failure, as many authors pointed out, and as repeated in Fitting's survey, the characterization of the negation failure in that case is the greatest fixed point. But in the new setting, which I'm proposing, this will be completely equivalent to least fixed point. Right? The program has been turned into positive and negative parts. When we compute the least fixed point of both parts, the least fixed point of the positive part gives you the least fixed point of what you had before. But the least fixed point of the negative part gives you the same thing as the greatest fixed point of the previous part. Also there is this equivalence. Well, I'm trying to compare Kripke-Kleene fitting semantics with what I'm doing. But to make this comparison, I need to adjust the universe on which Kripke-Kleene semantics operates. Originally, it was just the standard Hilbert universe. To make a comparison, I need to assume that it operates on the open version with its additional constants. And under this assumption, P is true in Kripke-Kleene fitting, if and only if P is a member of the least fixed point, however, P bar is not. Then P is false, if and only if P is not a member of least fixed point, but P bar is. And finally, P is undefined, if and only if neither P nor P bar are members of the least fixed point. And now, continuing with hierarchies, for these positive programs with equality constraints, well, P is a plus delta zero program with plus delta omega equality constraints. If the bodies of the statements in, I suppose that should be PC, this transformed positive version of the program, so another typo. If the bodies of the statements in the transformed version of the program are in such a class. And another important class of programs for further considerations will be plus sigma 1 with plus delta omega. No, not actually without plus. Plus sigma 1 programs with delta omega equality constraints. Now, for the programs in these classes, we define an operator T, which is analogous to operator used by Van Enden, Abt, and Kowalski. Obviously, it's order preserving. If you consider positive formulas, even if there are negative equality constraints in them, it is still order preserving. Then one can prove this property and also this property where C stands for Clark's completion. And the proof is analogous to Van Enden Kowalski's proof. Now, let's talk about non-continuity of such operators. If you consider plus sigma 1 programs, just a slight generalization of Horn programs, the related operators are continuous. However, what happens if you allow universal quantifiers in the program? I'm going to take a very simple program, just one clause, Q provided for all x, P of x. And recall that I have constants, k sub I, the free constants in the open Aberrant universe. And I'm defining a directed family of interpretations. In these interpretations, they go by levels for any n smaller than omega. At level n, I will have terms which I can produce starting from the free constants. I take an arbitrary free constant. I apply the function symbol f to it n times, where n is any number smaller than n. Then I plug in all such terms into the predicate P. The set of such atomic formulas is an Aberrant interpretation over the open universe of over the open universe of terms, and this is a directed family. Now let's notice that Q is a member of this. So if I take the union of all these families and then apply the operator, Q is there. However, if I take applied operator to a member of the family individually and then take the union, Q isn't there. So it's not continuous. And this means the earlier theorem doesn't apply. But curiously, if you look carefully at this example, the property of reaching the least fixed point in omega steps is not violated. And that's a good sign, maybe it can be generalized. Then I would like to mention that I will not have time, I think, to discuss details here, but using the use of the open Aberrant universe is crucial for that. If you take programs with universal quantifiers, even very simple ones, on the standard Aberrant universe, things do not work that way. For logicians, it's not. I mean, if we think about this is not terribly surprising, because these additional free constants which are available in the universe, well, if you look at them from the point of view of the syntax, they're like variables. And if you have a formula with a variable, well, you can universally quantify it. if you proved something about a variable, you proved the statement about anything. So this is what's behind these differences. I have never seen any, I mean, the results which I'm presenting go back to, I mean, there are some of the results from my dissertation from 1990, and I have never seen any, I didn't pay much attention to what was going in that area afterwards, but I have to say that I have never seen any work on open universes, and I think it might be an important area to explore. I mean, undoubtedly, the standard version of the aberrant universe is an important one, but there's this second branch which I think could be of value. Now, here's a theorem. Assume that P is one of the two classes defined before. Well, this means positive program with positive equality constraints, or positive existential program with arbitrary equality constraints. And now, if P is a program in one of these classes, and B is a corresponding formula, so also a formula with in such classes, then for every valuation V, if I iterate the operator on the open universe, omega steps, and B is true there with the valuation V, this implies that there exists a finite stage in the computation in these iterations where the same thing happens. So if something happens at the omega level, it happens at the finite level. Now, this is unique to open aberrant universes. In closed aberrant universes, this just doesn't hold. And the reason is, again, free constants are like variables and so on. Now, this leads to fixed point theorems. If P is in one of the two classes I specified earlier, then least fixed point can be arrived at in omega iterations. Also, this can be connected with the meaning of the program, because these two conditions are equivalent to B being semantically implied by P, or B being semantically implied by Clark's completion of P. And well, this is the kind of semantical implication which assumes that we restrict attention only to models, to interpretations based on omega aberrant universe. So we take arbitrary interpretations where the universe is the omega aberrant universe, and we say B is true in them whenever this is true in them. And to show more of the structure of the underlying reasoning, you may want to see how, for what part the assumptions are essential, the assumptions that we have this particular class of programs. Well, without these assumptions, 1 implies 2. Also, 2, 3, and 4 are equivalent. You do not need these assumptions for that. However, to have complete equivalence of all the conditions, you need these assumptions. And finally, here's an example of a +by1 program with delta 0 equality constraints, which has which violates these properties. And taking a careful look at this example, I mean, this program belongs to just one specific class, but if one takes a careful look at this single example is a counterexample showing that this desired property of reaching least fixed point omega iterations doesn't hold for any class other than the two classes I considered in this theorem. If I can take one more second, for the proof of the stepping down theorem, so the reasoning is this, I need a lemma. This will imply the stepping down theorem. If something is true at the stage omega, then it's true at the finite stage. And well, then the stepping down theorem implies the least fixed point theorem in one of the two forms. Now, what is this important lemma? The reasoning leading to the lemma is the following. Consider, for simplicity, languages without equality. And now take any positive program and a formula, and a positive formula B, any number n, any valuation v. Now, if at stage n of the iteration of the operator, B holds under some valuation v,